Okay, I think we left off talking about TCP, and specifically, I think we ended near this slide. So anyway, I want to start here because this allows us to review TCP, right? So remember, TCP, Transport Layer Protocol, main goal, end-to-end reliability, and part of the end-to-end reliability mechanism is something called congestion control, right? Congestion control is about you can think of it as a sender caring about the welfare of the nodes, on the path from the sender to the destination, right? And the main idea is you don't want to overwhelm those nodes, right? You don't want to cause, for example, the buffer of the intermediate nodes to fill up and overflow, leading to packet drops. Okay, because packet drops are bad for the sender, right? They're part of they cause unreliability, right? Now, clearly, if the sender, so let me ask you this: why can't the sender just communicate with the nodes in the middle, right? If it cares about them, like I care about you guys, and I always ask you, how are you doing? I ask you, do you have any problems? I ask you, do you understand? So why can't the sender do the same thing with the nodes in the middle of the network? Sounds reasonable or not? Yes or no? Does it sound like a good thing to do? There's some like why can't the sender ask the intermediate node, hey, how's your buffer doing? Is it full? Or if it's full, okay, I'll help you by backing off. Does that sound like a reasonable thing to do? So why doesn't the sender do that? Like, why don't we build a networking protocol to do that? Yeah?
If the buffer is full, then how are we making it without the question?
The sender, you mean?
What?
The sender?
No, if the buffer is full in the node.
Which node? Let's be precise about which node.
You said that the sender wanted to ask the node if its buffer was full.
Which node?
Somewhere in the middle.
Yeah.
And if the buffer is full, then it can receive that message, right?
Yeah, that's correct.
Is that why they don't do that?
Sorry, I missed your explanation. I thought you were just giving the setup. What's the explanation? I mean, the sender, my question is, why doesn't the sender ask the nodes in the middle of the network, meaning on the path to the destination, one of those intermediate nodes, why doesn't it ask them, are you congested? So right now it doesn't. So my question is, why doesn't it? Why don't you design a protocol to do that? So, and like, yeah? The paths are different, okay.
It's not fixed that they are going.
Okay, it's not fixed. How about you? Any ideas? It's not efficient, okay. Anyone else? I mean, we're worried about reliability. Why not? Why doesn't the sender just ask the nodes in the middle? Yeah?
Because if the node in the middle has a buffer overflow, then how is it going to receive a message saying, do you have buffer overflow? It can't
But, I could preempt it. I could periodically ask. Correct?
you still could, but in order to get a response, the node in the middle would need to receive your message going, are you okay?
Yeah.
And if it has a too full buffer, then how is it going to receive it?
But I can do it before the buffer gets full. I'm saying I can ask preemptively. For example, I ask you all are here, you seem reasonable, I ask you, are you okay? I don't wait until you get into the hospital and ask you, are you okay? Yeah?
Then possibly because by the time it receives the status from the node in the middle, the status of the node in the middle might change.
That's fine. But I mean, okay, if that what you're saying is true, but maybe I can live with that. I can get I can slightly delayed status. It's not fresh. So this is an interesting question. Okay. Yeah?
Is it because whichever will have that transport layer and layer 3 of maximum 2 to 3 layers, so the only transport layer for the nodes?
Okay, hang on. So
How smart are the nodes in the middle?
how smart are the nodes in the middle? So I think the two of you are getting there. Yeah, we're getting there. So remember, transport layer is an end-to-end protocol. And the way we've designed our network is end-to-end. Right? In fact, there's no intelligence in the middle of the network. So how smart you are is actually where I'm getting to. The nodes in the middle are just doing routing. Right? I mean, in some sense, for me to ask an intermediate node, I've got to address it, right? And I could address it, but we haven't designed our system like that. The internet is not designed like that. There's no reason why you could not, but in an internet, you will not. Okay, because we're end-to-end. So remember that. So that motivates the design of congestion control. It's done purely by the sender making inferences. Okay, later we'll see that there's been some attempt to try to do explicit congestion control. I'll say maybe 1 or 2 words about that in a couple of slides. All right, so are we okay with like these are ideas about transport layer design. It's not about the protocol, but these things also that you need to understand, right? So it's an end-to-end protocol. The sender is making inferences, and it's making inferences by probing the network, by sending packets in, increasing its rate of sending, and then seeing what happens. And then if there are bad things happening, if you congest the network, you back off. If you don't congest the network, you increase your rate. And that's what you see here. Okay, mainly in the AIMD phase. So additive increase, multiplicative decrease. The other thing to take away from this is, you see here, this is TCP Reno. Of the 2 bad events, timeout and triple duplicate X, these 2 events are treated differently. Right? We see that a timeout is treated much more aggressively by lowering the rate to 1 and then increasing again, using slow start to increase to half the threshold, and then you go into AIMD. The AIMD cut in half, right? So just to be very, very clear, this right here is a timeout, and this is the response to the timeout. This right here is a triple duplicate ACK, and the response to that is to cut the window size in half. Okay? Okay, so I hope you'll be able to articulate what's happening on this graph. That's one of the things you're required to do. Okay, you need to explain, because if you can explain it, you understand TCP. At least you understand TCP Reno. Okay, and then I mentioned yesterday that the different variants, you can have many, many different variants. And one of the variants, TCP Tahoe, basically treats timeout and triple duplicate X in the same way. Okay? Okay, now let's talk about AIMD. Why is this thing the right thing to do? So additive increase, multiplicative decrease, meaning when I increase my window size or my rate, I do it in a conservative way. When I decrease it, when bad things have happened, I do it aggressively. Why is this the right thing to do? The way we're going to understand that is I'm going to give you a graphical proof. I'm not going to give you a mathematical proof. We could do that, but the graphical proof is easier to see, and it's actually as rigorous. Okay? There's no hand waving here. This is, in fact, the core idea of the mathematical proof is here. Okay? So we're going to look at these diagram here, this kind of diagram. I'm going to assume a situation where I have 2 TCP connections or flows intersecting at an intermediate router. Okay? So there's a resource allocation problem. Okay, right? I have to decide how much of the... This thing keeps cutting out, right?
Just the once.
What?
Just the once.
Just once, okay. So I have to decide how much of the resource to allocate. Right? The buffer or the router has a resource. I have to allocate it between the 2 flows. So I'm plotting the rate, the rate or congestion window size of the 2 flows equivalently versus each other. So the x-axis is connection 1, the y-axis is connection 2. So this it's like a phase plot or scatter plot. Okay? Now there's nothing plotted here. On this plot, look at the blue dotted line. This blue dotted line is, let's say, the y equals x line. So I call this the fairness line. Why? Does anyone know why I call this the fairness line?
Both connections are the same
Yeah, on this line, x1 equals x2. Right? The rate for x1 equals rate for x2. So that's the fairness line. And the green solid curve I call the efficiency line. So suppose my resource is the outgoing link of the link rate of the router, right? So why is this line? This line is also a 45 degree line. So I call this the efficiency line. Why? Because if the outgoing link has a certain link rate, what's on this line? What can you tell me? Yeah, here x1 plus x2 equals the outgoing link rate. Okay, so that means I'm using the router at full capacity. There's no underutilization of the router. So on the green line, x1 plus x2 is a constant, and that constant is the link rate. And the blue dotted line is the fairness line, x1 equals x2. The intersection of those two is like kind of the optimal point, right? I'm fair and optimal. So, I mean, under this scenario, I want to operate, if fairness and efficiency are important to me, I want to operate at the intersection. Okay, and we're going to see that AIMD is the only adaptive way to get there. Okay, so we're going to show graphically that AIMD gets to the optimal point, no matter where you start. Okay, we're going to do that by this kind of curve. Okay, so let's say we start at the orange point. The orange point is my starting point. So that means at the orange point, x1 and x2 are such that I'm below the efficiency line, right? So what does that tell me? So now the assumption is that if the router is underutilized, there'll be no packet drops. And if the router is overutilized, meaning if I'm above the efficiency line, then packet drops will happen. Okay? Is that assumption okay? That makes sense, right? If the total sum is greater than the router can handle, something will have to. In fact, this is based on queuing theory. There's something called Little's law that says if the arrival rate of packets is greater than the rate at which packets leave, you get an unstable or unbounded buffer. Okay, essentially, if you are overloading the router, it will fill up and drop packets. Okay, so let's start at the orange point. So am I overloading or underloading the router? I'm underloading, right? Because I'm below the green line. Now, if I'm below the green line, there's no packet drops, packets are getting through, TCP is working as expected, and we're going to do linear increase because I'm getting X, right? Remember, we saw that in AIMD, for every time you get an acknowledgement or a window of acknowledgements, you increase your window size by 1. That's linear increase. So what's going to happen is, when I'm below the line, I'm going to increase my window size or my rate linearly. Both will increase linearly. So I operate on the trajectory is a 45-degree line, or a line that's parallel to this. Essentially parallel to this, starting here. So I'm going to increase my rate until I get above the efficiency line. Once I get above the efficiency line, now x1 plus x2 is greater than the constant, which is the link rate, and packets will get dropped. And how does TCP react? So let's say for the moment it's not timeout, I get triple duplicate X. Okay, you don't have to worry so much about like I said, you're mostly operating in the AIMD phase, right? So we're going to cut the window size in half. So now I'm going to make each of them drop in half. So if I'm here, what does it mean to cut my window size in half? If you think about it a little bit, you will see that what you want to do is draw a line from here to the origin and move halfway to the origin. That's the equivalent of both parties, both x1 and x2, cutting their window size in half, or cutting x1 by 2, x2 by 2. Okay, so what's going to happen then is, from this point, I'm going to cut it in half. I'm going to end up here. Now I'm underutilized again. Okay, and so I'm going to increase and so on. And I'm going to oscillate until what? What's going to happen? Notice I'm being pushed towards the fairness line, right? In this example, I'm being pushed towards the fairness line. Eventually, what's going to happen is this, right? This thing is going to eventually end up on the fairness line and just oscillate back and forth. Right? So TCP will constantly just oscillate around the efficiency line on the fairness line, which is what I said, pushing where I'm oscillating about the optimal point. Okay? Now, you might think this is just in this example. Well, start anywhere. Start anywhere on this plot. And you will see that you'll be pushed to the optimal point. Do you see that? Because every time you are above, you get pushed towards the origin. So if I'm here, I get pushed towards the origin, which pushes me towards the optimal point. Right? No matter where I am. Right? If I go here and I go here, I'll get pushed towards the origin, right? So I'm constantly, every time I cut in half, I'm being pushed towards the origin, closer to the optimal point. So if I'm to the left of the fairness line, I get pushed to the right. If I'm to the right of the fairness line, I get pushed to the left. Right? And the MD always makes sure if I'm above the efficiency line, I get pushed down. And AI lets me move parallel to the efficiency line, to the fairness line. So does everybody see that? The AIMD, so this is the sort of conclusion. AIMD is fair and efficient allocation of resources. Okay? So it provides a lot of stability to the network. So the question really is, so remember there's an increase phase and there's a decrease phase. And I gave you two options, additive and multiplicative. So there's 4 algorithms, right? AIMD, then there's there's AIMD, there's MIMD, multiplicative increase, multiplicative decrease. There's AIAD. There's also what? MIAD. I didn't write that because, well, I forgot. But you can check. So there's 4 options, right? So the question is, using this type of argument, this graphical argument, can you show that none of these other 3 don't get there? So let's try. Let's look at MIMD. So let's say I was here. Okay. No. So let's say Okay. So fine. So let's say I'm at the orange point, and I do MIMD. So what's MI? Multiplicative increase here. So I'm going to increase both. So I'm going to draw a line to the origin, right? Correct? So draw a line to the origin. And now I want to increase. I'm going to move away from the origin in a multiplicative fashion. So draw a line from here through the orange line, have it extend, right? And now I'm going to, let's say I multiply by 2 and decrease by 2, and multiplicative decrease by 2. So initially I'll start at the orange point and I'll move twice the distance away from the origin. Now I'm above the efficiency line. So what will happen? I'm going to do multiplicative decrease. Where will I end up? Back at the orange point. Right? And that's it. You just oscillate. So MIMD is not there. You can use the same argument to show that MIAD also doesn't work. Okay? And so the AIAD doesn't work, and MIAD doesn't work. Okay? So that's your homework. That's what you have to do. You have to convince yourself graphically, right, that, of course, AIMD, right? So again, the thing I want you to really understand is that for AIMD, you start at any point on this plot and run AIMD, you'll get pushed to the intersection of fairness and efficiency. Okay? And this, as I said, the mathematical proof takes a little bit of work, but it's just this idea made more explicit. Okay, so this really is the proof. Any questions? Yeah, anything?
Additive decrease. Such as subtraction. Additive increase.
Yeah. Yeah, so additive decrease. So let's look at AIAD. So AIAD will do what? So if you do AIAD, you will start here and you will move along this line, right? And then what's additive decrease? You'll just move back here. Again, it will just offset on this line. So we saw that MIMD and AIAD don't get you anywhere. Now it turns out MIAD does jump around, but it doesn't push you towards the middle. It actually pushes you away from the middle. Okay, so if you try to work out the fourth option, MIAD, it pushes you away from the middle. Okay? Yeah?
Isn't oscillating around the efficiency line also a bad thing?
Why is it a bad thing?
Because when you're above, you drop packets. When you're below, you're not using the link properly. Or you're not using the link to its maximum efficiency.
Yeah.
So, you don't really want oscillation, or rather you want to keep the oscillation as small as possible.
Yeah. This is an interesting point. The thing to understand is that efficiency line is constantly moving. It's actually, if it was a constant and you actually knew what it was, you could build a new protocol that just tells the two senders what their rate should be. Correct? But you need to adapt. So the point is, no matter where the efficiency line, in some sense, is changing, and so this will adapt to it. It will constantly push you to wherever the intersection of the two is.
Does the oscillation dampen over time? Considering a more or less stable efficiency.
Yeah. Yeah. I mean the oscillation. So some of that will depend on what your protocol is, right? What's the slope of your increase and so on. But if you're just increasing by 1, yeah, it's not going to be too bad, right? So, yeah. I mean, so you won't drop too many packets, right? But of course you will, for example, for the multiplicative decrease part, you will drop halfway. So there are more efficient things you could do if you knew, but the fact is you don't know. Yeah. One, you don't know what it is because, so I gave you a kind of an example of one router and two connections. But actually, this thing is happening in a distributed way at all routers. But the similar argument, you can extend it to the entire network. Okay, so is everybody okay here? So the point is, AIMD is fair and efficient. Okay, all right. Let's wrap up TCP. So congestion control is a cycle of actively probing the network, causing congestion / packet drops / triple duplicate acts, and then backing off. And doing this in a continuous way so you can adapt to network state, which is dynamic. So I mentioned that right now we are doing, taking an inference approach. The sender is making an inference about congestion. There are sometimes you can do other things, which we didn't talk about, but there are protocols that kind of look at that. If you see a trend in your round trip time, you can also make an inference, right? Because the queuing delay is a function of the number of packets in the queue. Okay? That means the greater the number of packets, the longer the delay, right? The longer the round trip time. So if you see a trend that the round trip times are increasing, that can give you some information. And you can exploit that to kind of make an inference about congestion. You can, now there's two other, now if you can make an inference about congestion, so, okay, sorry, so that's at the sender. So I'm just saying that's another signal that we didn't discuss. okay, which is looking at the trend of the round trip time. Now at the intermediate router itself, there are some things that routers itself can do. So this is now introducing some quote unquote intelligence inside the network. So there are two mechanisms that are worth looking at. One is an implicit way of doing congestion control. So if I'm an intermediate router, if my buffer is filling up, then I take some action. Maybe I proactively drop packets. So there's a protocol called RED, random early dropping, okay, which is essentially saying and so what this does, if I drop packets before my buffer fills up, then I can control what I drop, and that is a sign, an implicit signal to the sender, right? Because the sender is looking for bad things to happen, right? Okay, so I can do random early dropping as an implicit signal. Some protocols use some free bits in the header to do explicit notification of congestion. So an intermediate router will set a congestion bit, right? So there's a bit that says, if I'm an intermediate router and I'm getting congestion, so I want to send a signal to the receiver, right? I will set that bit. Now, the thing is, there is just one bit. So if any of the routers sets it, the sender just gets to know that one of the routers in the path is getting congested. But then the sender can actually act on it. Okay, so there's a variety of things that people have proposed to try to deal with congestion. But the core protocol on the network is still TCP, with congestion control being inferred or done at the sender by doing congestion inference. Okay, the rest of the slides are there to show you, to give you a summary of TCP. I'm not going to go over it, but it talks about the TCP socket, the TCP header, and the finite state machine for TCP. So if you wanted to implement it, this is what you would implement. Okay? Okay, so then, so this wraps up our discussion of the end-to-end reliability mechanism, and specifically about TCP. So as I said, these are transport layer protocols. These are the mechanisms for end-to-end reliability. We talked in depth about TCP, and if you want more details, is chapter 3 of Kuros and Ross. And there's, just to have another reference, there's a networking book by Peterson and Davey, and this is chapter 6 and 7 of that. So any questions? Okay, what I want to do is, because this is a good time to ask some questions. I don't know why it always does that. But I haven't even opened it. I guess it's okay. I can do as read only. I think it should be fine. I don't want to edit. Okay, so what I want to do now is, so remember, TCP was an end-to-end, or transport layer is end-to-end. This end-to-end principle is a huge part of the design of the internet. Okay, but I'm going to question it. We're going to aggressively say maybe it's the wrong thing to do. Okay, and we'll see why. Okay, so I cannot stand this. It's okay. So these slides, I should be give credit. There's a clean slate design internet project out of Stanford, and specifically there's a researcher there. He's a collaborator of mine, Balaji Prabhakar, and he has some thoughts on this, and I have taken his thoughts. Okay, so the two examples I give are completely his. They're his papers. Okay, so the question this end-to-end principle is the idea. I think I talk about it here. Okay. So this paper by Salzer, Reed, and Clark, I've uploaded it to the Luminous files. Okay, it's under supplementary. this talks a little bit about the design of the internet, and they talk about this end-to-end argument. So the question is, when you want to implement a function, where do you implement it? And it turns out that the internet has been designed by putting all intelligence, all the intelligent functions happen at the endpoints. The intermediate nodes in the network don't do end-to-end things. Okay, that's why, for example, I think we discussed this. We said that a router, a core router in the internet, only implements up to network layer. It doesn't even implement a transport layer or an application layer. That's another reason why in the current internet you can't talk to an intermediate router. You can't say, hey, I want to address you. Okay? So this end-to-end argument says that you should implement the function at the endpoints. The middle of the network is dumb. The smartness exists at the endpoints of the network. So this is this argument, and if you think about it, this allows you to change things a bit more rapidly, right? If you want to change application, you can. You just download a new application. I don't need to change the entire core network. Okay? So it's allowed the internet to scale. Okay, I think opening it up in Read has... Okay, let's see if this is better. Yeah, it's better. Okay, so now I've gone through telling you that this end-to-end principle, where you implement intelligence at the endpoints, has been responsible for the success of the internet. So why question it, right? Because that's what I want to do. I want to question it. I want to say maybe we should have some intelligence in the network. The main reason I want to do this has to do with how the network is being used. Before sort of current, let's say, the current usage scenario of the internet, the internet was being used to transmit packets. And in fact, much of our discussion centers around packets, right? But if you look at how we use the internet, right, we send streams of packets. So when you have a teleconference call, right, there's a stream of packets from sender to a destination. Yes, that stream consists of packets. So treating everything like a packet still works, right? And this end-to-end principle works well when you have packets only. Okay? But we use streams of data, or I call them connections or flows, right? We talk about a TCP flow. There's a whole bunch of data going from sender to destination. Now, when you have flows, the current internet works, but perhaps there's a chance to make it more efficient. Okay? And then so that's the idea, is we recognize packets, or intermediate routers recognize packets because they have to do routing. But they don't recognize flows. Right? They don't recognize the fact that two packets are from the same flow, part of the same process, communication between sender and destination. And so what I want to introduce is the idea of flow recognition. Okay, that's the questioning. Okay, there's a whole bunch of applications of this. I'm going to talk about two. Okay. Okay, the first example is a very simple example. It's called bandwidth allocation. So you have a router, okay, and I'm showing you the buffer at the router, and I want to be fair. So let's say there are 3 flows, and I want to give each flow a fair allocation of the memory space of the router. So solution 1 is fair queuing, meaning I keep track. Oh, So there are three flows here, red, green, and blue. So a packet comes in. Oh, you're from the red flow. Okay, I give you a space. Oh, you're from the blue flow. Okay. And I keep track of it. And I ensure fairness. I ensure that everybody is getting an equal amount. So none of the different flows can get more. This is expensive because I got to keep track. I've shown you an example of three flows, but a router can handle thousands of flows. So this will slow down the router significantly if it has to keep track. Okay? So this is, again, this motivates why intermediate routers are dumb. They look at the network layer header and make a routing decision. They're optimized. When we talk about network layer, we'll look at the internals of a router, and we'll see what functions a router has to do. They're optimized to do that. Basically, it's a switching decision. How do you map from input interface to output interface? Okay? Things like this are very expensive, where you have to keep track of who I'm serving, which flow they belong to, when there could be thousands of flows. All right? So there's an idea. Maybe I just do FIFO. Right? So this is expensive. One idea is just do FIFO. You let everybody come in and you serve them. Well, what can you tell me? So FIFO buffers, meaning first in, first out. I just serve packets on a first in, first out basis, and I do TCP at end hosts. So I say it doesn't work. Why? So look at it. Who's dominating the buffer? Which flow is dominating the buffer? Red. So first of all, it's not fair because it depends on opportunistic arrival of packets. But that's not the real problem. Because you could argue that, well, if green doesn't want to use the buffer, why not allow red to use it? In fact, that's the idea behind statistical multiplexing, right? Why not be efficient? Opportunistic use of resources. So what's going to go wrong? Anybody know? When the buffer fills up, what's going to happen? Packets will get dropped, right? Now suppose the next packet that comes in is green. What's going to happen? Green will get dropped. And what's the consequence? You already know. You studied it, right? I said it's TCP at end hosts. What's the end host that's hosting the green flow going to do? No, it's going to do something first. What's congestion control in TCP? Yes, it's going to do retransmission eventually. But what is it going to do first? Back off. Right? And what is that going to allow red to do? Dominate more. So that's why this doesn't work. Right? If you happen to drop green or blue, it's going to just allow red to dominate more. Now, it gets even worse if red is a UDP flow and doesn't react to its own packet drops. UDP doesn't react to packet drops, right? And so here I said they're all TCP. Even if we're all being TCP, there's a very good chance you'll drop either green or red, green or blue, and those will back off even more. Okay, so this doesn't work. So this is how the current internet is, right? The current internet is FIFO with TCP at end hosts. This is expensive. Is there the question I want to ask, is there a middle ground? And it turns out there is. Okay, we'll look at our first attempt. The first attempt is this. In fact, I'm gonna do it from here. The first attempt is, now this is going to be something the router does, not the end host. Okay, the router. The first attempt at solving this, this is like solution 1, 2. So I want to now allow the router to take some action, and the first attempt at the action is as follows. I'm going to randomly sample from the buffer and drop it. So this sounds good because if I randomly sample this buffer, which packet is more likely to get sampled? Red. And that's good, right? I want to drop red because red's hogging the buffer. Sounds like a good thing to do. It turns out that it almost works. The problem is there's too high there's the chance of getting green or blue and dropping them, because we're not doing flow identification, I'm doing random sampling, is still too high. If I sample red or blue and drop it, again, that's going to affect the TCP at that end host and cause it to back off. So this doesn't work. The same problem as before. You allow red to dominate more. So the second attempt does something similar, okay? But instead of sampling one packet, you sample two. You sample two packets. If they match, you drop both of them. What you're basically doing is increasing the probability of sampling red, and hence decreasing the probability of sampling green or blue. It turns out that from an engineering point of view, this works. Okay, and this was in a paper called Choke. I forget what the acronym stands for, but this is a paper by Prabhakar and his research group. They showed that this leads to fairness. Okay, now notice this. You're not keeping state, right? All you're doing is you're randomly sampling the buffer, but not keeping state. But because you're doing random sampling and red is dominating, you're more likely to choose red and allow the buffer to be equalized. Okay? So this is Choke. Yeah, this is Prabhakar, Pan, and Sunis. And it basically penalizes dominant flows. The cool thing is, what these guys did was they made this work practically. Okay, it's called approximate fair dropping, AFD, and it's implemented in the Generation 2 Cisco routers. Okay, so they actually work with Cisco and it's implemented at intermediate routers. So it's kind of cool. Okay, so one example of where we are allowing, now in some sense we are violating something, right? Because we are trying to identify flows that are dominant. Okay, so I call this in the direction of flow recognition. It's not really flow identification, but it does violate the end-to-end principle. But it leads to massive performance increases. And they made it work without keeping a lot of state. In fact, keeping no state. Okay, so it's kind of cool. The other example I want to give you is, I call it elephant traps. Elephant traps, so some people call large flows with a lot of packets, elephants, and flows with very few packets, mice. So for example, if I'm just surfing the web and clicking at links, that's a mouse. If I'm downloading a movie or watching something on YouTube, there's a lot of flows in this, a lot of packets in this flow, that's an elephant. Okay, and again, this gets to, can you identify elephants using random sampling? Okay, so the idea is, okay, so again, we're going to do random sampling. If you, for example, like if let's say you have a flow of size X, and I'm going to sample it with a kind of a biased Bernoulli distribution, like a biased coin, right? That has a so if I flip a coin, if it comes up heads, I kind of target this packet. And a large flow will have approximately, a flow of size X will have 1/10 chance of being sampled, right? And so the question is, so most short flows will not be sampled, and most long flows will. So how can we use this to, again, to be fair at an intermediate router? So the comparison will be to a system that doesn't do this. So the top system, you have a queue. So this is the buffer at an intermediate router. All the flows go into one buffer, and they get served in a FIFO manner. In the second system, I'm going to sample, and I'm going to split. So if a flow is sampled, it goes into the long flow buffer. If it's not sampled, it goes into the short flow buffer. And I'm going to compare these two in terms of latency. Okay, so that's the goal. Do we get it? This is my random sampling, which is now, in some sense, violating the end-to-end principle, because I'm trying to separate long flows and short flows. So let's see what happens. So again, it's very simple. In fact, it's even much simpler than Choke, right? Which had to do a comparison. There's no comparison here. There's just sampling. Okay. So this is what we get. So this is from the paper, again, the same group. Okay, their algorithm is called SIFT. Okay, and we're plotting here the overall delay. So on the x-axis is load. So this is the rate at which I'm pumping data in. Okay, so load on the x-axis, and on the y-axis, I'm looking at delay, average delay. Now, there are three curves here, but why don't we ignore the green and red curve are almost the same. They are just different variants of SIFT. So let's ignore the difference. We just look at the blue curve, which is original, and maybe the red or green curve, it doesn't matter, which is SIFT, the random sampling. All right? And we see that what happens is, over all the flows, the average delay decreases. So now notice we were fair in that I had a buffer of size b in scenario 1, and each of the two buffers were of size b by 2. So the total amount of buffer space remains the same between the two. So it's a fair comparison. Okay, so this is good. But you might say, actually, maybe this is over all short and long flows. But maybe over the long flows, you're doing worse, right? So let's look at that. So this is the average delay for just the short flows. So this is good, right? This makes sense. A long flow is going to be sampled more often. It gets put into the long flow buffer. Now, the router is going to just do round robin between the two buffers. Okay, it's not like we prioritize one of the long flow buffer or the short flow buffer over the other. Okay, so what this tells you is that mice now don't get trapped behind elephants, right? Because you look at as the load increases, we see that the gap between SIFT and the original grows. And you got to remember, this is on a log scale, right? You look at my y-axis is on a log scale. So there's almost, over 1 order of magnitude, over 1 order of magnitude gain. Okay, so you might say, okay, short flows benefit, but maybe it's the long flows that suffer, right? So let's see what happens with the long flows. The long flows don't suffer. In fact, this could be due to statistical validity. I'm not sure, but if you look at this, for much of the load, even the long flows are benefiting. It's slightly lower than the original. My takeaway from this, my interpretation of it is that the long flows don't get affected much. So this is good, right? You don't affect the overall average delay for the long flows, but you significantly benefit the short flows. And how are you doing this? You're doing this by doing something intelligent in the middle of the network. Right? You're trying to do effectively flow identification without keeping state. Okay? Now the good thing is IPv6. We'll see when we look at the header for IPv6. IPv6 has an explicit flow identification field. So in addition to having, all the other stuff like packet, sequence number and all this stuff, there's an explicit flow identification field. So now in IPv6, we can identify flows directly. Okay? So right now, we don't really see what has been done with that, because the current implementations of IPv6 they're meant to be kind of an evolution from IPv4. Okay? So long flows here. Yeah, so the conclusion is that this end-to-end principle was good. We studied it, but maybe it's time to evolve. All right, and the two examples I gave you are evolution of that in the constraint of the current internet. Okay, but with the next generation internet, which allows flow recognition, people can innovate. All right, there's going to be lots of innovation happening to try to improve performance. Okay, and then I think my idea was that it leads to new cross-layer design mechanisms as well. Okay, so with that, I want to end talking about transport layer. Okay. What we still have to do, we still have a couple more things to do. We'll do that on this coming Monday. I want to wrap up the question of why we have reliability at the two layers. Okay. I want to talk about some problem solving. So you should now be able to look at the homework on transport layer. If you have questions on that, I'll answer it on Monday. Okay. The third thing I want to do is I want to talk about the throughput of TCP. Okay. So and for that I don't have slides, but I'm going to use the visualizer. So we'll look at the throughput of TCP and do some problem solving. Okay. Thank you very much. If you have questions, I'm up here. I'll see you on Monday.